Let's extend our knowledge of stoichiometry into titrations. Now remember, in a titration, we slowly add a solution in the burette, known as a titrant, into our Erlenmeyer flask filled with the unknown sample, or the titrand. We continue to add the titrant until a complete reaction occurs to the equivalence point, and this is usually indicated by a change in the color of the sample or the endpoint. And ideally, the endpoint should be at or very near to the equivalence point. When we do a titration in a redox situation, however, the endpoint, the color change, occurs because there is an excess of one substance over another, and this substance is often colored. Now, as a quick reminder, the equivalence point is when you have the exact number of moles of both reactants, so you have no excess reagent over the other, whereas the endpoint is the point where you stop the titration, and this is indicated by a color change of your mixture. In a redox titration, one of the samples, in this case the titrant, will always be the strongest oxidizing agent or the strongest reduction agent. In Chemistry 30, most of our experiments are unknown, will be our reducing agent, so that will be the substance that gets oxidized itself, and that will be in the Erlenmeyer flask. Whereas our known, our compound in a burette, will be the strongest oxidizing agent. It is very common in our Chem 30 course to use potassium permanganate or potassium dichromate, because these are both colored compounds. When there is excess of either of these compounds, the solution in the sample will turn color. One of the common oxidizing agents we use is potassium permanganate. Potassium permanganate, or actually permanganate itself, is a very dark purple compound. When in the presence of acids, it will often undergo reduction into manganese 2+ ion. Manganese ions itself is a colorless, very, very slight pink compound. So therefore, when you have any excess left over potassium permanganate, the entire solution will turn pink or even a dark purple. On the other hand, we can use potassium dichromate as well. Potassium dichromate is a orange compound, and again, in an acidic environment, it will get reduced into chromium 3+ ion, and chromium 3+ is very faint green. So at the endpoint, any additional dichromate causes the solution to stay orange. So in summary, when you have excess permanganate left over, the solution will turn purple or pink, and when you have excess dichromate left over, the solution will turn orange. Both of these color changes is the endpoint of your titration. That is when you should stop adding titrant to your sample. Unfortunately, when it comes to redox titrations, our oxidizing agents are somewhat unstable. Therefore, we have to standardize or find a concentration of that solution before we actually use it. So the standardization is to determine the exact concentration of the titrant. The way we do that in Chem 30 is to titrate our strongest strongest oxidizing agent with another what's called a primary standard. This is a solution that we can just create moments before the titration. It has an exact concentration so that we can use the exact concentration of our reduction agent to determine the concentration of our oxidizing agent, which remember will be either permanganate or dichromate. And please refer to your Chemistry 30 booklet or textbook to determine how to prepare such a solution. A quick summary is that you need to calculate the mass of the primary standard you need to weigh out in order to make a solution of precise concentration. Then you need to dissolve that amount in a small amount of liquid and then dilute it to the appropriate volume and then ensure the mixture is properly mixed. So let's now do a sample calculation for I have a titration of a redox reaction. In this example, we are given the concentration of the potassium permanganate, our strongest oxidizing agent. That means that we do not have to standardize it because it was already done for us. However, in your lab and in your questions, you may have to do a double titration to first determine the concentration of your potassium permanganate, and then use that concentration to determine the concentration of your unknown reduction agent. So, in our example, we have 11.3 mils of a 0.0203 mole per liter potassium permanganate solution, and we use it to titrate 25 mils of a unknown concentration of sodium iodide. And we're asked to find a concentration of sodium iodide. So just like all of our previous redox reactions, we have to determine the strongest oxidizing agent and the strongest reduction agents. And after listing all our species and determining whether or not they're oxidizing agents or reduction agent, we find from our table of half reactions that acidified permanganate will be our strongest oxidizing agent, whereas iodide is our strongest reduction agent. Next, we go to our table of reduction half reactions and write out the reduction reaction here, and read our reduction reactions backwards, determine the oxidation reaction, circled in red here. We notice that for every reduction, there's 5 electrons transferred, but for the oxidation reaction, there are 2 electrons transferred. Therefore, we need to find the lowest common multiple between 5 and 2, and that is 10. That means we need to have a total transfer of 10 electrons in our reduction reaction. And to do that, we need to multiply everything by 2. And then for the oxidation reaction, we also need to have 10 electrons, and to get that, we need to multiply everything by 5. After we do that, we add everything up, cancel the electrons, and this is our final equation right here. Now we need to determine the moles of permanganate, the strongest oxidizing agent that we actually use. We were told from our question that our concentration of permanganate was 0.0203 moles per liter, and we used 11.3 liters. Multiplying by those together, we get 0.000229 moles of permanganate used. Now we have to do some stoichiometry, determine the number of moles of iodine present. Our coefficient is going to be 10 over 2, or from our balance equation. So then we multiply that to find out we have 0.00115 moles of iodide. Now we use the volume of sodium iodide that were given to us, 0.0250, divide that to find that our concentration of sodium iodide is 0.0459. We can also do a bonus step. We can determine the concentration of iodide in our final solution. Well, again, doing stoichiometry based on the number of moles of permanganate and a new coefficient or ratio, we find that the moles of iodine is 0.00573. We now need to divide by the total volume, and we know that we use 0.250 liters of the sodium iodide and 0.0113 liters of the permanganate. Those volumes are now added together because they're both present in the Erlenmeyer flask. And we find that the concentration of iodide at the end of the titration is 0.0158 moles per liter.